Welcome to the video part 2 for the unit 3 in computer vision. Geometric intrinsic calibration. Intrinsic and extrinsic calibration can be computed at the same time. And in intrinsic calibration, we use the internal camera calibration parameters, and in extrinsic calibration, we use the poses of the camera. The classic approach to the camera calibration is as follows. The calibration patterns, and this shows a 3-dimensional target and this shows a 2-dimensional target. Span the calibration object as much of the workspace as possible if a smaller calibration rig needs to be used. Estimate the covariance in the parameters to determine the quality of calibration. One of the more reliable ways to estimate a camera's intrinsic parameters is in photogrammetry. It is common to set up a camera in a large field looking at distant calibration targets whose exact location has been pre-computed using surveying equipments. Intrinsic parameters. Intrinsic parameters describe the conversion from unit focal length metric to pixel coordinates and the reverse. This is the matrix for the conversion. It is common to combine the scale and focal length together as they are both scaling factors. And we have to note that the projection is unitless in this case. The picture shows the intrinsic camera parameters measurement. This is the physical retina at which we observe the object, that is, this is the pinhole through the pinhole camera. So the perspective projection, this is the point P, X, Y, Z, and U and V are the intrinsic camera parameters, where F is the focal length. We need to take into account the dimensions of the pixels. And the center of the sensor chip may not coincide with the pinhole center. So these two may not coincide. This is the center of the chip. And the camera coordinate system may be skewed due to some manufacturing error. And in homogeneous coordinates, this is the matrix for the intrinsic camera parameters, where we have the 5 parameters which are known as the intrinsic parameters. The UV, X, Y, Z. So it is a simpler form of notation. P equals 1 by Z, K, 0, into K0 matrix into P. With this P is with respect to the camera coordinate system, that is X, Y, Z, 1. This is K0. This is your K and the column 0. Extrinsic camera parameters. So translation and rotation of the camera frame with respect to the world frame. In homogeneous coordinates, this is the way we represent the coordinate system. So it's further simplified too. So we are having UV1. So we have a 3x4 matrix with 11 degrees of freedom, where we have 5 intrinsic parameters, 3 rotation parameters, and 3 translational parameters. So the R denotes your rotation parameters. The camera's intrinsic and extrinsic parameters are found using a setup with known positions in some fixed world coordinate system. So U, V, the camera parameters, X, Y, Z is the coordinate system. So the 5 parameters. So the applications are first down line and then virtual advertising in the grounds, normally in the playgrounds. Parameters of a stereo system. We have intrinsic parameters which characterize the transformation from camera to pixel coordinate system for each camera. We have the parameters like focal length, image center, and aspect ratio. Extrinsic parameters which describe the relative position and orientation of the two cameras, and the rotation matrix is given by capital R and the translation vector is given by the capital T. So R, T, which gives the relative positions from where. This is the first position and this is your next position. Relative positions between the two position of the cameras. and this gives the essential matrix for a calibrated camera and the pictures to represent how your calibration is being made. And the next is the equations fundamental matrix for the uncalibrated camera. And in camera calibration, we determine the camera parameters from known 3D points or calibration objects. We determine estimate the focal length and optic center and triangulation and post estimation. So for this, how will we note down all these 3D points or calibration? So you do with internal or intrinsic parameters such as focal length, optical center, aspect ratio, and by using which kind of camera you are going to use it. Next is for external or extrinsic camera, which is used for the post estimation. So here the parameters describes where is the camera and how can we do this. So the different camera calibration approaches are possible approaches are linear regression least squares, nonlinear optimization, vanishing points, multiple planar patterns, and panoramas, which gives the rotational motion of the camera. So this is the image formation equation. So F is the focal length, and this is the camera coordinates, external coordinates x, y, z, and your camera parameters u and v. So this is rotation and this is the translation. R denotes the rotational matrix and this is the translational matrix. And this is the calibration matrix notations. So this form, if your K is your K good enough? So how you decide it? You decide up with the, you won't have any non-square pixels if you take a digital video of it, and screw rate and radial distortion should not be present. Like that you have to determine your K. So fold intrinsic calibration matrix K and extrinsic post parameters R, T together into a camera matrix. So M equals K into R/T. The R is the rotational matrix and T is the translational matrix. So put 1 in the lower right hand corner for the 11 DOF parameters. Directly estimate the 11 unknowns in the M matrix using known 3D points xi, yi and zi and measured future points ui, vi, and the equations of ui and vi is given. So in linear regression, bring the denominator over. So how you are going to determine this? So equate it and then you will be making and find the values of it. So you have to find the least squares, that is using the pseudo inverse. Will this be good enough for calculation of it? So the future measurement equations, ui equation and the equation of here vi, where we use the likelihood, that is your M has been given. So this is the likelihood equation for the matrix M. And in optimal estimation, this will be the log likelihood of M, which is given in terms of the set of, for the set of points ui, va, the equation of C. And how do you minimize C? You use nonlinear regression least squares because ui cap and vi are nonlinear functions of M. And in Levenberg-Marquardt method, iterative nonlinear least squares are used. So linearizing measurement equations are given where you substitute your log likelihood equation. And iterative nonlinear least squares, we solve for the minimum, dou C by dou M is equal to 0 and A into del M equals B. So this is the equation for the Hessian and error. So what if it is not getting converged? So multiply the diagonal by 1 plus lambda and increase lambda until it gets converged. And half the step size del M, and then use line search. So the any other ideas also can be used for the converge. So how you come to an conclusion is use the uncertainty analysis and find the covariance. Summation equals A inverse. So find the inverse of it. Then you have to find out whether maximum likelihood is the best idea and how to start in vicinity of global maximum, global minimum. And in advantages of this is very simple to formulate and solve, and it can recover K of R slash T from M using QR decomposition. And the disadvantages present here is it can't compute the internal parameters, and if you have more unknowns than the 2 degrees of freedom, then this method cannot calibrate easily, and it needs a separate camera matrix for each new idea. Separate intrinsics or extrinsics, new future measurement equations. This is your new equation for U and V in terms of I and J. So here we will be having K, Rj and Tj. We use the non-linear minimization standard technique in photogrammetry, computer vision and computer graphics. Separate intrinsics or extrinsics. How do we parameterize this R and del R? So use Euler angles, which will be a bad idea. You can use quaternions. We will have 4 vectors on unit spheres, and use incremental rotations where R of I plus del R. You increment it and replace it with your R. And you also update with the Rodriguez formula. This is your equation for the del R. And the advantages, we can solve for more than one camera pose at a time and potentially few degrees of freedom. And the disadvantages of it is having more complex update rules, and it need a good initialization to recover this K from the M. In multiplane calibration, we use several images of planar target held at unknown orientation. You compute the plane homographies UI VI1, which is this equation, and you are approximating it into H into X. You solve for K inverse transform and K inverse from H case of H case. One plane if only F is unknown, 2 planes if F, UC and VC are unknown, and more than 3 planes for full finding the value of K. So if you want to take a picture, this is your way how you are going to grab your picture. Light is falling over the object and get reflected, and it falls over a photosensitive material. So the projection matrix, how you calculate is, it is your F into X by Z into and F into Y by Z. So F is the focal length and X, Y, Z are your axis parameters in your calibration which you are doing in the 3 axis. So Fx, Fy, X, Y, Z. So this is the projection matrix of the any picture capturization. So in single view ambiguity, given a calibrated camera and an image, we only know the ray corresponding to each pixel. So here we don't have enough constraints to find which is the position of the X. So you can see it, but you don't know exact position of the X. So this leads to the single view ambiguity. So this is an example of it. Your actual position, apparent position of a pattern. See here the person is standing with some of balloons with her hand, and here when you are single ambiguity, see here the person is holding the roof itself. So this is how your ambiguity plays here. This is also an example of it. And the creating an 1D picture, here you can see the shape is quite different in way of arranging it, where in the shadow sculptures you can see the exact patterned display of them. So how you resolve this single view ambiguity? Either you should light lasers out of your eyes, which is not possible and is also biologically plausible and dangerous. So how to solve this? You take 2 different calibrated cameras in different views. This is for one angle of a view, this is another angle of view, and which will solve the X, that is the 2 views get intersect at a point, and you define that this is the position of X. Instead of doubting all the positions, now you get a conclusion of what is the position of X. So this is in your human stereopsis disparity. So this is the way how you fix it. So human eyes fixate on point in space. You rotate so that the corresponding images form in the center of the fovea. So we have 2 eyes. So both left eye and right eye, when you do it, it gets correctly, when we view an object, it gets correctly pointed to the fovea. This is how the computer vision is designed, so that how the natural human eye is working on. So fix it up to position and get an image of it. So disparity occurs when eyes fixate on one object and others appear at different visual angles. Then you will be having two different focusing points over it. So stereo photography and stereo views. So you take two pictures of the same subject from two slightly different viewpoints and display so that each eye sees only one of the images. So this is a way how you do it for stereo photography. And these are the some of the example picturization as years pass out. So how you resolve it? So you find out this R comma T, that is you fix up the two position and you find out and conclude the position of your X. So one option is move and find the correspondence of it. So if you know how you moved and how you have calibrated the camera, you can easily solve for the position of X. So knowing R and T, how do you know that how far you have moved? So either from vision and also you can using your ears you can come to conclusion. So that's the reason why we have three ducts in the ear. So we can solve via signals sent to the muscles and you can come to a conclusion. So where is the position? So we have some pictorial cues like shading and texture of the surfaces, then perspective effects. All these are the pictorial cues. In the familiar objects, you use all these pictorial cues and come to a conclusion of what you see. So if you see a monitor, okay, probably this much is the width of it, probably this much is the height of it. So if it is a table or desk, it is probably flat. So this way you can infer the image what you have seen. So reality of 3D perception is, 3D perception is absurdly complex and it involves integration of many cues. So learned cues for 3D are used and stereo between eyes is then stereo via motion, then integration of known motion signals to the muscles and acceleration sensed via ears and past experience of touching objects. All these will be used for 3D perception and all connected. The learned cues from 3D probably come from stereo motion cues in large part. So how are all these cues combined? So image illusion persists in a weaker form even if you have stereo vision. So guessing the texture is rectilinear is usually incredibly reliable. Multi-view geometry problems. So calibration, we need camera intrinsics K in order to figure out where the rays are. So these are an object and you are fixing up where it is viewed in 3D. So from camera 1, your position is R1, T1 and from camera 2, the positions R2, T2, that is your rotation and translation matrix. So from this, you fix up where you are going to find out this point. So in stereo epipolar geometry, given two cameras and find where a point could be. So motion, we find out, you find out the R and T for a set of cameras given correspondences. So in this equation, this is the equation for your P and here your X is a 3D point which is 4 cross 1, that is your X, Y, Z 1. And then this is the rotational matrix, the 3 cross 3 matrix, and this is the translational matrix, 3 cross 1 matrix, and F is your focal length and U, V are your principal point which are your image coordinates of camera origin on retina. Just moves the camera origin and then you find out your parameter P. So your P is the 2D projection of a point X. So this is the camera calibration you use. So now you convert it into UV1 and M3 cross 4. So after this you will be having XYZ1. So all these are now equated to M3 cross 4. So if I can get pairs of XYZ and U comma V, then equations to constrain M, then I can get all these values. So how will I get XYZ and U comma V? A funny object with multiple planes. So using tape, you measure known image coordinates and the known 3D locations. and a set of view planes for different objects, and given n points with known 3D coordinates xi and known image projection. You estimate the camera parameters. So this is the equation of it. So from this geometry, which implies mxi into pi are the scaled copies of each other, where your pi equals lambda into mxi, lambda is not equal to 0. So from homographic fitting, this implies that their cross product is 0. So pi cross mxi equals 0. So this is the equation, that is your projection points m into xi. So after all processing, we get the final matrix equations to be this. This is the linear method. So how many linear independent equations we have? 2. And how many equations per u comma v x y z pair is present? Again 2. So if m is 3 cross 4, then how many degrees of freedom we have? So 11 is the degrees of freedom. So this is the matrix, and we solve all this and we get the minimization of these arguments, and eigenvector of A transpose A with smallest eigenvalue is calculated. And we degenerate these functions. An example, all points will be on one plane, that is an issue, and if we need multi-plane targets to resolve this. So pull a fast one, that is we will be having this as our final equation, then we can find the P. So what's the difference between KR and T? The solution is to find KRT and M, that is solution is to find QR decomposition on the leftmost 3 cross 3 matrix. So finite options of a upper triangular matrix into this rotation. So if Pi equals Mxi is over constrained, then the objective function isn't actually one you care about. So instead, you initialize the parameters with linear model and apply off-the-shelf nonlinear optimizer to this equation. So that what are the advantages we get is we can also add radial distortion, and you cannot optimize over known variables and add constraints. So how do we get this? Give some projection Pi of unknown 3D point X in 2 or more images with known cameras Mi, and then you find the X. So thank you. This is the end of the part 2 of the video.